In 4.5c, we're going to tie in two things that you've already done. So we've already done definite integration, and remember that's just integrating when we have limits on it. So just a quick little recap of that. If I was integrating from 1 to 3, just an easy function to find the antiderivative of, the fundamental theorem of calculus says we do the antiderivative, and then from 1 to 3, the 3 goes in first, then the 1, and we subtract those. And we've done that already. We've already done the process of u substitution with an indefinite integral. So indefinite doesn't have the limits, but we've talked about if you have a composition of functions, you can use u substitution to write it in a form that you can easily find the antiderivative of. So using this u substitution process right here, I can now write that as sine u, and then I'd have 1/2 du, and the antiderivative of sine is negative cosine. So I'd have negative cosine u, and we did some back sub, and then plus Carl. So we have done definite integration and the fundamental theorem of calculus, and we've done u substitution. We just haven't combined them and done a definite integral with u substitution. We've only done them separately, so I'm going to do it a little differently than how it's explained up here. So we'll just do a couple examples. So when you go and approach this one as you normally would, you don't know the antiderivative of this. Now, if the root wasn't there and it was just x times 1 minus x squared dx, then I don't need anything fancy because I could just multiply this in and be on my way. On your worksheet, there's, I don't know, I think like 4 of them where you don't need u sub. But when you do, we're going to start it as normal. We'll let u equal 1 minus x squared. And then my du is negative 2 x dx. And so far, nothing's different from what you've done before, but we want only x dx, so we do a negative 1/2 fraction correction. Here's the only problem. When I go set up my new integral, I have root u, and then I have negative 1/2, and then I have du. However, these limits are limits for x. They would be the span along the x-axis if I were to graph this. And I can't have limits for x in an integrand involving u. You have to have a variable match. So the only thing you need to do is right at the beginning when you define u, you're going to change the limits so that they are for u. So when x is 0, u is 1. When x is 1, u would be 0. So now I have everything, including the limits, in terms of u. And then what I can do is the fundamental theorem of calculus, which says to do the antiderivative. So we add 1 to the exponent, getting 3/2. We divide by that exponent, which would cause us to multiply by the reciprocal. I have the negative 1/2 fraction correction out front, and I go from 1 to 0. Then what that allows me to do is have a negative 1/3, and as long as I change the limits, I don't have to back substitute my u choice back in because my limits are for u. So as long as you change those limits, you can just dump it in right here and get the answer of 1/3. Keep in mind that had this been calculator active, you could have math 9'd it right from the beginning, and this on a calculator would have come out as 0.3 repeated. But you wouldn't have a calculator for one like that. So we'll do one more with that process on this front side of the sheet. So there is no way for me to do the antiderivative as this stands. So I notice that I have a composition of functions on the bottom, and so I have my u be x squared plus 4. But because I have a definite integral with some limits, I'm going to go and change those limits right now. When x is 0, u would be 0 squared plus 4. When x is root 3 on the top, u would be root 3 squared, which is 3, plus 4. So these are my new limits. Sometimes it helps to cross them off to know that you aren't going to use those anymore. You're changing everything to be in terms of u. So now my thing is I need to get this x dx part in terms of u. So I say the derivative of u with respect to x is 2x. So du is 2x dx. I don't want that 2 in there, so I do what we've always done. Do my little fraction correction. So now I'm at the point where I'm going to rewrite that integral. I'm going to go get it back so I can see it here. I have got an integrand that has a root of my u choice. It's got a 1 x dx on the top. X dx is a half, so I'm going to have a 1/2, and then this would be the du. Because again, if you were to kind of put a 1 there and then put the x dx off to the side, this right here, oops, sorry, is 1/2 du. So when we put the half out front. But remember, if I want to just work with u and not have to back substitute, I have my limit going from 4 to 7. And now I just do it as normal. I'd be integrating from 4 to 7, u to the negative 1/2 technically. I add 1 to that exponent, getting a half. I divide by a half, which is multiplying by 2. I have the 1/2 out front, and I'm going from 4 to 7. These cancel, and I end up with u to the 1/2 with a 7 going in, so that would be 7 to the 1/2 minus 4 to the 1/2, and that would be my answer. Now just to kind of show you what you could do also, at this point, and don't put this in your notes, but had you not changed these limits, so suppose you didn't do a limit change and you were going to go from 0 to root 3. So suppose you said, I'm going to go from 0 to root 3 instead. That's actually legal, but the difference is those are limits for x, so you would have had to go back in and put x squared plus 4 in for u and then use those old limits. So if you don't change the limits, and then you'll get the exact same thing. You'll get 7 to the 1/2 minus 4 to the 1/2. So the answer would work out. So this changing of limits allows you to skip one step, and that's the back substitution part. On the next page, we'll do a couple with some trig. So on this one, this is a composition of functions. My u choice would be twice x. To avoid having to back substitute, I'm going to change my limits. So I'm going to be going from 0 to 2 pi halves over 4, or pi over 2. So my limits I'm going to change, and then I'll never back substitute. So my du will be 2 dx. I don't want that. I want it to be sine u du. So I'm going to do a 1/2 du will replace the dx. So all of this now gives me a new nicer integral. I'm going to integrate sine u, then dx is 1/2 du, and my new u limits are 0 to pi halves. Now I do the antiderivative of sine. And remember, you've got your sine, cosine, negative cosine, sine. So you should write that so you don't goof up. But the antiderivative, which moves you up the scale, would be a negative cosine. So I do negative 1/2 cosine u evaluated from, not these, and that's why it helps to cross them off so you know you've changed them, from 0 to pi halves. And then I like to put the negative 1/2 out front, and I do cosine pi over 2 minus sine of pi over 2, minus cosine of 0. Cosine pi halves is the x value up at pi halves, which is 0. Cosine of 0 is the x over here, which is 1. So that'd be 0 minus 1, leaving me with a positive 1/2. What you really should do, though, is take out your graphing calculator and go math 9 this, and your calculator will give you that 0.5. You wouldn't have a calculator, but I want you to know that that option, if presented to you, you should use math 9. We're going to skip that number 5, and we're going to go right to 6. When you have a sum like this that's not integratable as it stands, you're going to break it up. So you're going to go from 0 to pi 6th of 1 dx plus from 0 to pi 6 of the rest of it. And I probably won't finish this one, but I'll start it. This one right here, no need to do anything fancy. You know the antiderivative of 1 with respect to x is x. I don't need to change the limits because there's no u sub. So what this applies to the actual answer would be pi 6ths minus 0, or just pi over 6. That matches graphically, by the way, because remember, this is the function y equals, or f of x equals 1. And when you're up at 1, and you're integrating from 0 to pi over 6, let's say pi over 6 is right here. Remember, we're finding the area under the curve, and the area of this rectangle would be a 1 by pi over 6 rectangle. So it would supply pi over 6 to the integrand. So it works geometrically too. Then, for this one right here, I'm going to have to use some u sub because I don't know the antiderivative of this product. So I'm going to let u equal sine x. The minute I do that, because I've got limits, I'm going to change them. Sine 0 is 0. Sine pi over 6 is 1/2. So these are my new limits when I set up my integral. My du is cosine x, which is the rest of this. So I'm basically sitting there with u du, which is really nice. It's just u du from 0 to 1/2, which is going to give me u squared over 2 from 0 to 1/2. 1/2 goes in first. 1/2 squared is a fourth. Cut it in half and you get 1/8 minus 0. So my final answer is the pi over 6 from the first part of the integrand plus the 1 over 8 from the second part of the integrand. And that would be the last one. Example 7, you can't do with u substitution. We can't integrate absolute value as it stands. We need to be clever and break it up. So let's take a look at what the graph of this looks like and see how we would tackle that. This part inside the absolute value bars is an upside down parabola up at 1. It hit the x-axis at 1 and -1. But the absolute value part makes every part where it was going to go negative, which is from 1 on, and it pops it up. So instead of continuing down like this, the absolute value pops that up. And we're integrating from -2 to 2. So we're finding the area. You might say that's a triangle. This has got curvature, so it's actually not. We're integrating under that, but somehow I have to do it without the absolute value bars. So remember what we do with that. Everywhere it went negative, you're going to pop it up. And to mathematically pop it up, you're going to take the opposite of it. So from -2 to -1, you're not going to integrate that as it stands because that would be negative. You want to pop it up and make it positive, so you take the opposite of it. And the opposite of it is x squared minus 1. Or you could put a negative out front and keep it as 1 minus x squared. This is just cleaner. From -1 to 1, you can go ahead and use this as it stands because it's positive, so you don't need to switch the integral. But then from 1 to 2, again, you need to do the opposite or pop it up. You can either subtract it or add its opposite, which would be x squared minus 1. Either will be mathematically correct. Now I've got it in a form that if I had to, I could integrate it because I know the antiderivative. I just do that from -2 to -1 plus, and I would go do a whole bunch of arithmetic, and I'd be done. So the assignment is worksheet 4.5C. If you are absent and don't have access to that, I posted the key in Schoology, so you can just get the problems off of there and do it on notebook paper. You are allowed to skip 2 of them that I don't know what they are. I'm almost done, Sophie. I'm going to find the ones you are allowed to skip, and then I will sign off here. It'd help if I could find them. I can't find the worksheet from yesterday. All right, so you can skip the whole first page 157 because that was these examples I just did. So those examples 2 through 7 on the front page, just go ahead and cross the whole thing off. On the rest of the set, you can skip number 15 and you can skip number 18. All right, so that's it for 4.5.